Good morning, students. In the previous lecture, we have completed the first chapter, that is modeling of systems, right? There we have studied mechanical systems and electrical systems, right? And analogous systems. Okay, next in the second chapter, that is block diagrams and signal flow graphs. Yes, what are the topics that are going to be covered in this lecture? Just I will brief you out. The transfer functions, already briefly you have studied the transfer functions with respect to mechanical systems, and also we have solved, we have obtained the transfer function for the electrical networks in the previous chapter, right? Okay, then here we'll be studying the block diagram algebra and block diagram reduction rules and how to obtain the transfer function, that we will see. The next signal flow graph and it is a mathematical procedure or method, right? We will be using the mathematical formula in order to obtain the transfer function, right? And we'll solve few numericals based on both the block diagram reduction technique as well as signal flow graph, that we'll be seeing one by one. Okay, first we'll start with the block diagram, right? So we can define the block diagram as it's a pictorial representation of the functions performed by each component and of the flow of signals. Okay, just if we will take the example of liquid level control system, right? Okay, liquid level control system. We can observe here in liquid level control system there is a tank filled with water, right? And there is a controller which is responsible for opening and closing of this valve, pneumatic valve. Whenever this valve is open, the water will flow into the tank, right? Whenever the valve is closed, the water will not flow into the this tank, right? And there is a float in order to measure the liquid level in the tank, right? This float is responsible for measuring the liquid level in the tank. If the tank is full, then this valve has to be closed. So if the tank is full, then the controller will issue the command to the pneumatic valve so that the valve is closed and the water will stop flowing into the tank. If the water level goes down, means if the drain is open, if the output is open, the water level will decrease. If the water level decreases, then the controller will issue the means the level of liquid in the tank is reduced. So in order to maintain the desired level or actual level in the tank, the controller will open the pneumatic valve and the inlet valve where the water will flow into the tank and it will achieve the desired level, right? Okay, here we have to identify, we know any of the control system, closed loop control system has controller, plant, right? Controller, then actuator, plant, then feedback element or right? Feedback element. Okay, we have to identify which is controller, actuator, plant and feedback element here, right? Okay, we'll take one by one, right? Yes, controller, this is the controller, right? This block is the controller. Then actuator, right? And float is the feedback element, right? It will tell feedback element, float is the feedback element, right? The controller. Then what about the pneumatic valve, opening and closing of the valve, right? So this acts as an actuator. So I'm drawing the arrow mark here. This acts as an actuator, right? Then tank itself is a plant or process. This tank, right? This is the tank, and this itself is the plant or process or mechanism, right? Here it is the plant. Okay, and float is the feedback element. And we will try to draw the block diagram of the liquid level control system. We have identified which is controller, which is actuator, which is plant and feedback element. And next we will draw the block diagram of the liquid level control system. I hope this example is clear to you, right? And we have defined the block diagram. It is a pictorial representation of the functions performed by each of the component and of the flow of signals, right? We will see how to represent this scenario or the liquid level control system in terms of block diagram representation, right? Okay, we have identified the tank is the plant here, the controller, and here the valve, the pneumatic valve, that itself is the actuator, and float, the ball here, the float is the feedback element, and tank is the plant, right? We'll see how to represent this liquid level control system in the block diagram form, right? If you see any of the block diagram, it consists of 5 basic elements, right? One is blocks. Yes, it has to contain blocks. The transfer functions. Second is the transfer functions of the elements. Yes, this will come to later, right? What is transfer function? How it is represented, I will tell you later. Then summing points, takeoff points and arrows. Right now, summing points we know, but takeoff point we don't know. We'll define it later. Summing point, takeoff point and arrows, right? So all these are the 5 basic elements any block diagram consists of, right? Okay, this is the liquid level control system. Now we will represent this in the terms of block diagram, right? Okay, controller, yes, we have represented. pneumatic valve is the actuator. As I told no, pneumatic valve is the actuator. Then tank is the plant, right? Okay, controller, pneumatic valve is the actuator. Then tank is the plant. Okay, what is the input? The desired level of water in the tank is the input, and output is the actual level of, right? What is the actual level of water in the tank? Then we will sense the actual level of water in the tank through the float, right? So float is the feedback element. We have identified, right? Float is the feedback element. Based on the float position, we will come to know whether the actual level of the water is equal to the desired level. That we will see, right? So actual level, and we want to always maintain the liquid level, means actual level and desired level should be same. If they vary, then the feedback is taken, and suitably the valve, the pneumatic valve is either opened or closed, and the water is allowed into the tank, or it is not allowed into the tank based on the opening or closing of the valve, right? And here this is the summing point, also we call it as error detector or comparator or summing point, right? And here this we call it as takeoff point. Here this one means, here you can observe, here from the output it is going to the another block, means the signal will go concurrently to other blocks, right? So this we define it as takeoff point. We'll define it once again later, but right now you understand this is takeoff point, right? And this is the summing point. I hope you understood. If any doubts, please unmute yourself and speak to me so that I can clarify your doubts. I hope you came to know how to represent the liquid level control system in terms of block diagram, right? This is how we represent. So input is desired level, output is the actual level, right? Controller, pneumatic valve, tank, and this is the float position, is the feedback element. Okay. Yeah, similarly, we can, and this block diagram representation is not unique. It depends, but the functionality should be same. But block diagram representation is not unique. It varies from person to person. Overall, the functionality should be same. Here, if it is the liquid level control system, all will draw this only. If it is complicated system or complex system, then slightly the representation in terms of block diagram may vary from person to person, right? So the representation of block diagram is not unique. And one more thing is, the block diagram is possess the unilateral property. Unilateral property means, you can observe here the desired level, the input, the signal is flowing like this. You can observe in one direction, from this block to this block, right? From input to output, it's going like this, right? Is there anything coming back here, right? So block diagram is possess the unilateral property. The signal flows in particular direction or single direction, right? Okay. And these are the arrows, also we call it as branches. From one block to another block, the line joining this arrow marks, and the line, this we call it as branches. That we'll see it later, right? Okay, next we will see the simple closed loop system. Also we can call it as simple closed loop system or canonical form of closed loop system. Right, we know how to represent the closed loop system. In the first chapter we have studied the open loop and closed loop systems, right? So same block diagram here that has been drawn here, right? So simple closed loop system. Yes, G of S is the forward path transfer function, H of S is the feedback path transfer function, R of S is the reference input or simply input, and C of S is the output, right? Also we call it as controlled output. And here, yes, feedback signal, B of S, I'll write it here. So okay, I'll remove here. Okay, feedback signal. Let me assume that it is negative feedback. So I'll write it as minus, and R of S, we will add it. This is the summing point. And E of S is the error signal. Okay, we have defined what is what. So where R of S is Laplace transform of the reference input, because we have represented everything in terms of Laplace domain, right? Not in time domain. So R of S is the Laplace of reference input, and C of S is Laplace of the controlled output, C of t, and E of S is the Laplace of the error signal, E of t, and B of S is the Laplace of feedback signal, B of t, and G of S is the forward path transfer function, and H of S is the feedback path transfer function, right? Okay, these things we know, right? Any of the closed loop system can be represented in this form, right? Next we'll see how to derive the transfer function of the simple closed loop system. Next, that we'll see, right? So the derivation of the transfer function of the simple closed loop system. Okay. Okay, once again, the simple closed loop system. This is the block diagram of the simple closed loop system, right? And the arrow mark we have seen. Finally, what we have to get? We have to see here there are two blocks here, input and output. There are two blocks, and here the error detector is there, also called a summing point, and takeoff point. All those things are there. From here we are converting it into, there is only one single block. It has input and output. Means we have reduced two blocks to single block. If there are multiple blocks in the block diagram, we have to reduce it to single block consisting of input and output. So, and obtain the transfer function, right? So, how to obtain this, that we will see. How we will get this, that we will see, right? So, the single block has the transfer function g of s divided by 1 plus g of s into h of s. The input is r of s and output is c of s, right? But how to obtain this? How to derive the transfer function of the simple closed loop system? We will see one by one. Okay. First, C of S. How we will get C of S? Just observe here. C of S is nothing but the error signal E of S into G of S. That is written here. G of S into E of S. Call this as equation 1. Is it fine? Then next, the feedback signal B of S. This is the feedback signal B of S. Right? How we will get this feedback signal? Here, the signal that is coming into H of S block is C of S. C of S into H of S. So B of S is nothing but C of S into H of S. So we have written here B of S is equal to C of S into H of S. Call this as equation 2. Next, the error signal. Yes, we will come see we are coming from output like this. Here, first we are taking C of S, then B of S, then E of S. C of S we have written the equation. We have called it as equation 2. For B of S we have written the equation and we have called it as equation 2. And next we will see E of S. What is E of S? R of S minus B of S, right? So R of S minus B of S. Call this as equation 3. Okay, fine. Next, what is C of S? From equation 1, we know that it is G of S into E of S. G of S into E of S. What is E of S? E of S from equation 3, it is R of S minus B of S. Substitute here. So we have substituted R of S minus B of S for E of S, right? G of S into E of S. We have substituted for E of S. That is R of S minus B of S. So multiply this G of S into R of S minus G into B. G of S into B of S. So this first term is written as it is G of S into R of S minus G of S written as what is B of S from equation 2. You can refer equation to B of S is C of S into H of S. Substitute here C of S into H of S. Substituted here. Then separate the C of S terms one side. C of S is here. So C of S, C of S. Separate it. Take this side. Take this side. It will be plus and take out C of S. So C of S is equal to 1 plus G of S into H of S. This is left as it is. G of S into R of S. So the transfer function is the ratio of output to input, right? So we want to obtain the transfer function C of S by R of S. So C of S, take this R of S this side. C of S by R of S is equal to G of S divided by 1 plus G of S into H of S. This is the transfer function what we have obtained, right? Of the simple closed loop system. So this is the transfer function of the simple closed loop system. Okay, fine. You can observe here, we have taken the negative feedback system. So the input signal R of S is positive and feedback signal B of S is minus, negative. Most of the systems, whatever we consider is negative feedback system only. Suppose instead of negative, suppose there is a positive feedback system plus, then what are the changes in the transfer function? Just observe here. Just the sign will change. Instead of, so if it is negative here, we will get plus here. Just observe the position. If it is positive feedback system, we will get minus here. So plus or minus. I can write it as plus or minus. Here it is minus plus. Here it will become plus minus. If it is negative feedback system, we will get positive. If it is positive feedback system, we will get minus 1 minus G of S into H of S. Right? So I have enclosed it in the square bracket. Sorry, block. C of S by R of S is equal to G of S divided by 1 plus or minus G of S into H of S. If it is negative feedback system, 1 plus, it is not plus or minus, 1 plus G of S into H of S. If it is positive feedback system, 1 minus, in the denominator I will get 1 minus G of S into H of S. Right? We have seen the derivation of the simple transfer function of simple closed loop system. So and we can represent it like this, right? So whatever we have obtained, we will represent it in a block G of S divided by 1 plus G of S into H of S. The input is R of S and output is C of S. So this is the transfer function representation of the simple closed loop system, right? Consisting of single block. From 2 blocks, it has reduced to single block, right? So you should remember what is the transfer function of the simple closed loop system. For negative feedback system means you have to tell it is C of S by R of S is equal to G of S divided by 1 plus G of S into H of S for negative feedback system. You should remember this, right? Okay. Next we'll move. Yes. Block diagrams and transfer functions of multivariable systems, right? We'll see. Suppose we have seen there is only one input and one output. Suppose there are more than one inputs, what to do? That we'll see next, right? So block diagram and transfer functions of multivariable systems means more than one inputs, right? That we'll see. Here, for example, we'll consider two input linear system. Means we'll consider there are two inputs for the linear system, right? There can be three inputs, four inputs, five inputs, and so on, multiple inputs. But what we are studying is we are considering two input system. So consider the two input linear system shown in figure this 3.4a, this one, first one. You can observe here R of s is the input, this is the summing point, g1 of s is the forward path transfer function, and one more summing point is there, and we are adding one more signal here, another input u of s. R of s is one input and u of s is another input. Okay, then g2 of s is the forward path transfer function, and c of s is the output, and feedback element is h of s, right? We are considering the two input linear system. R of s is the main input and another input u of s. Let us treat this u of s as a disturbance signal. It is not, you can treat it as another signal, or we will treat u of s as a disturbance, right? So I have shown here, let us treat the u of s as a disturbance signal, right? So totally two signals are there. Then how to obtain the transfer function and how to analyze these kind of systems whenever there are two inputs, multiple inputs or multivariable system, right? Okay, for first we'll assume that yes, in the first diagram, this is first diagram, and in the second diagram what we are doing, we will assume that u of s is 0. Means I will assume u of s is 0. Assume u of s is 0. Means this u of s is 0 means this summing point will vanish. So we will redraw this block diagram, and it is as shown in figure 2. This is figure 1. Then next this is figure 2. Right? Yes, the summing point vanishes. You can see here. So R of s, G1 of s, G2, everything remains the same. Right? Then we will try to obtain the response of the system or transfer function of the system. What is transfer function of the system? The output to input, CR of s divided by R of s, right? CR of s divided by R of s. I will get something, numerator by denominator. Some numerator terms I will be getting and denominator terms I will be getting. Is it fine? Okay, fine. Observe here. Okay, then can I, if I want only the response of the system, means CR of s I want. So if I want only response, CR of s is equal to some numerator term will be there divided by denominator term will be there. This R of s will come this side into R of s. You are getting, right? This is the response of the system. Why I am calling it CR of s means because u of s is 0. If u of s is 0 means the response of the system is due to the input R of s. Hence I will call it as CR of s. It indicates that the other input is 0. U of s is 0. The only input for the system is R of s, and corresponding to this input R of s, the response is CR of s. So CR of s is equal to numerator by denominator. Some terms will be coming that I will be telling what are the terms that will come into R of s. I can write, is it fine? Then observe here, we know the just now we have seen the derivation of the transfer function of closed loop system. See here, in the forward path g of s is there, in the feedback path h of s is there, and it is, let me assume that this is negative feedback system. So c of s, the ratio of output to input will give me the transfer function. C of s by R of s is equal to g of s divided by 1 plus g of s into h of s. This we know. So we will make use here. Okay, in the forward path there are two blocks, g1 of s into g2 of s. If the two blocks are in series, are in cascade or series, this we call it as series blocks or cascade blocks. I can multiply and make it single block, g1 into g2, right? So this will become single block. I will write it here, just observe here, g1 into g2. I am not writing g1 of s into g2 of s, just I will write g1 into g2. It is understood. So this block I will remove, this block I will remove, means it has been converted into single block, g1 into g2. And another block h of s. Just compare with this, g of s is here, g1 into g2, and h of s same. So the transfer function CR of s by R of s is equal to g divided by 1 plus gs. What is g here? G is g1 into g2. So g1 into g2, g divided by 1 plus gh. G is nothing but g1 into g2, right? G divided by 1 plus gh. And CR of s is equal to numerator by denominator into R of s. So this is numerator term and this is denominator term, and this is CR of s. Divided by R of s, we have taken R of s this side. I hope you are getting, right? Okay, next, in the third diagram or figure 3, what we are assuming here is, assume r of s is 0. We'll assume r of s to be 0. In the second figure, we have assumed u of s as 0. We will assume r of s to be 0 here. Fine. Okay, we'll assume r of s to be 0 and we will redraw the block diagram from figure 1. From figure 1 to figure 3, how we will get, we'll see. Observe here, u of s is present, but r of s is 0. So we will rearrange it. See here, u of s is the input, it goes to summing point. From input to output, I should move and make it a straight line. U of s, and this is the summing point. G2 of s is the forward transfer function, C of s. So this first we will represent this. We can observe here in figure 3, u of s, summing point, G2 of s, and Cu of s. This C of s is nothing but Cu of s here, because we have assumed r of s to be 0. If r of s is 0 means the response or output of the system is due to the input u of s only. Hence we call the response as Cu of s, because the response is due to the input u of s, because we have assumed r of s to be 0. Okay, this path is taken care. U of s, G2 of s, C of s. You can observe here, U of s, G2 of s, C of s. Then remaining, from output, it goes to the feedback element h of s. Since r of s is 0 means this summing point vanishes, but minus sign is there. Please take care of this minus sign. So h of s and g1 of s, they will come in series, right? H of s into g1 of s, and it goes to summing point at the input, the summing point here, h of s, g1 of s, but this minus sign, because of this minus sign should not be ignored. So this minus sign is taken care here. I hope how to redraw the figure from diagram from figure 1 to figure 3, assuming RS to be 0. I hope you got it. If any doubts, you can ask so that I can repeat once again. I hope you are getting. How we draw the block diagram is, input should be on one side, output should be on the other side. Input on left side, output on right side. We have to draw like that, because u of s we have rearranged from figure 1 to figure 3. Right? Next, just compare with this figure 3 with this simple closed loop system, g of s and h of s. Here g of s means g2 of s. H of s means these two are in series or cascade, so we can make it a single block by removing these two blocks. I can write it as g1 into h. It is g1 of s. I will not call it as g1 of s and h of g1 into h. I will call it as. So I will remove these blocks g1 of s, h of s. I will remove it, and I will make it single block g1 into h. Yes, g1 into h I have made. So you compare with this. In the forward path, I have g of s. Here it is g2 of s. Here it is h of s. Here it is g1 into h. So we know the transfer function how to write, cu of s by u of s. So cu of s by u of s is equal to g divided by 1 plus gh. G means g2 here. G2 divided by 1 plus gh. G2 into g1h. G1h. It is written here. So this is cu of s. Cu of s. And u of s is taken this side only, right? I hope you understood. U of s, actually it will come here, but we have moved it here. I hope you are getting. So call this as equation 2. This is equation 1 and this is equation 2. So equation 1 is the response due to only the R input, and the equation 2, it is the response only due to U input, assuming R of s to be 0, right? Okay, next. But in the figure 1, you observe there are two inputs, R of s and U of s. In figure 2, figure 3, we have considered only one inputs. Next, if I want the total response of the system, then I will make use of the principle of superposition, and I will add figure 2 and figure 3, means CR of s. C of s is equal to CR of s is here, and CU of s. CR of s plus CU of s is equal to C of s. Right? CR of s plus CU of s is equal to C of s. I hope you are getting. We will make use of that. So the total response of the system, C of s is equal to CR of s plus CU of s. We have the equation CR of s here in equation 1, CU of s. Add it and take common, this we will get. This is C of s. I hope you are getting, right? Then next, we have to make some conclusion or some, yes, we have to observe something and make some analysis. We will see by looking at equation 1 and equation 2, and we will let some things to be greater than 1, all those things we will see, right? And we'll make some analysis. Okay, now we will assume that g1 of s into h of s, the magnitude of, you can observe here, magnitude of g1 of s into h of s is very much greater than 1. This condition we are going to take, and another condition is magnitude of g1 of s into g2 of s into h of s is very much greater than 1. This is second condition. These two conditions we will make use, right? Okay, always I will not call it as G1 of S, G2 of S into H of S. Just I will read it as G1, G2, H. G1, G2, H. I will read it like this. And here I will read it like this. G1 into H. Right? Okay, we are taking two conditions. G1 into H is very much greater than 1 and G1, G2, H is very much greater than 1. Then at that time, what will happen to equation 1 and 2? This is equation 1. We are considering U of S as 0 and this is equation 2 considering R of S as 0. So how it will affect, we will see. We will consider equation 2 first. G1 into H of S is very much greater than 1. G1, G2 into H of S is very much greater. We will apply these two conditions for equation 2. First we will take equation 2. G1, G2, H of S. It is very much greater than 1 means this 1 can be neglected. Because it is very much greater than 1 means this 1 is very small. So I will neglect this. So this 1 is neglected. In the denominator I have only G1, G2 into H of S. Then G2 of S, G2 of S will get cancelled, right? G2 of S, G2 of S get cancelled. What I am left out? G1 into H. But we have assumed another condition. G1 into H is very much greater than 1. So in the denominator G1 into H, it is very much greater than 1 means let me take it as infinity. Very much greater than 1 means I will go to infinity. I will consider this as infinity. Anything divided by infinity is 0. Means what I am getting? Cu of S is 0. If I take these two conditions, G1 into H is very much greater than 1 and G1 G2 into H is very much greater than 1. I am getting Cu of S to be 0. Equation 2 Cu of S becomes 0. What is the meaning of this? Just observe here. Cu of S divided by U of S. It becomes 0. And the effect of disturbance is suppressed. That is what I want because we are treating U of S as a disturbance, right? So the response due to disturbance should be 0, right? It should not give any response. If I treat one of the signal U of S as disturbance, if I assume these two conditions, G1H is very much greater than 1 and G1 G2H is very much greater than 1, I am getting the transfer function Cu of S divided by U of S as 0, right? Means from this what we came to know is that effect of the disturbance is suppressed. This is the advantage of the closed loop system. This is the advantage of the closed loop system. Means the effect of the disturbance is reduced. And we have seen in the comparison in the first chapter differences between open loop and closed loop. Right? The disturbance is less affected in case of closed loop as compared to the open loop. The disturbance heavily affects the output of the open loop system. But in the closed loop system, it is suppressed or reduced effects of disturbance. This we have proved here. Right? This is case 1. Next, we'll move to case 2. Here, case 2. Yes, and we are taking these two conditions, same condition. G1H is very much greater than 1 and G1 G2H very much greater than 1. Now we will apply these two conditions for equation 1. For equation 1 means we are assuming U of S to be 0. So we will apply here. Just take this equation CR of S and take this R of S this side. CR of S by R of S. G1 G2H. This is very much greater than 1 means this 1 can be neglected. This 1 is neglected. Right? This vanishes. So G1 G2 cancels. G1 G2 cancels. So what I will be getting? I will write it here. CR of S divided by R of S is equal to what I will be getting? G1 G2 cancels. So I am getting 1 by H of S from equation 1 after applying those two conditions. Let's say, right? CR of S by R of S is equal to 1 by H of S. Whenever there is only R input, U of S is 0. We can observe here. This is a transfer function. Whenever there is only R input, there is no U input. There are two inputs, R and U. But here, there is only R input. U of S is 0. So the transfer function of such system is CR of S by R of S is equal to 1 by H. We can observe here, it depends, it is inversely proportional. The transfer function is inversely proportional to the feedback element. And it does not depend on G1, G2 blocks here. G1, G2. It depends only on the feedback element H of S. Right? I hope you got it. Yes? So the closed loop transfer function becomes independent of the forward path transfer function G1 and G2, but it is dependent it is inversely proportional to the feedback element H of S. Right? This is one of the observation what we are making through this. So the closed loop transfer function I have written here. The closed loop transfer function becomes independent of G1, G2 and becomes inversely proportional to H of S. Right? This is the second observation. In first observation case 1 what we have seen? The disturbance is suppressed. In the second observation we have seen the transfer function is inversely proportional to the feedback element and it is independent of the forward path transfer function G1 of S into G2 of S. Okay. Just I will pause. If any doubts, I will address, or else I will move to the next topic. I hope nobody is asking any doubts. Okay, I will move to the next topic. Yes, we will not concentrate much here. If there are more inputs, multiple inputs, multiple outputs, how to represent? So, multivariable system, it has multiple inputs R1, R2 till Rp of S, and multiple outputs C1 of S, C2 of S, and CQ of S. Rest, we will remove this multivariable system, and instead of multiple system, single line, we can make use of this symbol R of S, it indicates multiple inputs, and this symbol C of S, it indicates multiple outputs, right? Okay, we can write it in terms of summation. The output is summation of all the inputs multiplied by the transfer function of this system. So G of S, G into R. The transfer function is G here, G into R. So G into R, right? So in terms of summation, I can write, or else I can write down in terms of vector matrix, or in matrix form also I can write. Matrix form. Okay, we will not worry much about this because we will not be studying the multivariable system. We will concentrate only on single input, single output systems. And also max at the max, we have seen the analysis here. We have considered two input linear system. At the max, we will be having two input linear system, not more than two. We know how to handle such situation using the principle of superposition, right? The next, yes, block diagram reduction. We have seen what is block diagram, right? We have defined what is block diagram. It is a pictorial representation of the functions performed by each of the component, right? And of the flow of signals that are indicated, right? Okay, next, block diagram reduction. Why we are calling it as reduction? This is very important. Block diagram we know. Why block diagram reduction? You can observe, I have taken one example here. This is representing some of the system here, some of the control system. I don't know which control system. It is representing some system. It is having several blocks. In the forward path, means from input to output, if I move like this, from R, there is one summing point, another summing point, G1 block, one more summing point, G2, G3, summing point, and C. This is forward path. So several blocks are there, G4, H2, H1, and multiple feedback paths are there. See, from output through H2, one more feedback path, another feedback path, multiple feedbacks are there. So, and I want to convert this entire block diagram. I want to reduce this block diagram using the block diagram reduction rules. There are set of rules, block diagram reduction rules, so that I can reduce the multiple blocks to a single block. So this red arrow mark I have shown how. So this is a single block. To the left there is input R, to the right there is output C, right? So, and this is the transfer function. After reducing this, the transfer function is indicated within this block. So this is the transfer function what we have indicated, G1, G2, G3 plus G1, G4 divided by something, this entire thing, right? So finally what we are doing, we will reduce it to a single block, and there is input and there is output, and we will represent the transfer function inside the block. This is the transfer function what we have indicated here. I hope you are getting. Yes, and always each and every block, within each and every block we represent that particular block by we will write the transfer function within each and every block, right? Okay, how to reduce it we'll see. I hope you came to know what is block diagram reduction. By using the set of block diagram reduction rules, we will eliminate multiple feedback elements, multiple blocks into a single block, right? Single block consisting of transfer function having input to the left and output to the right, right? So we'll see the block diagram reduction rules and block diagram algebra. That we'll see it later, right? Next, we'll see the block diagram algebra here. What is block diagram algebra? I'll tell you. Just observe here. The diagrams are self-explanatory, but still I will go through it. Okay, figure A. Let me take this figure A, right? So there is summing point here, right? This we call it a summing point. Yes, there is one of the input R of t and another input is C of t in time domain. There we have represented in the same diagram both time domain representation and Laplace domain. First we will concentrate only on time domain equations. R of t is the reference input, another input is C of t plus they have indicated. Then E of t, error signal is R of t plus C of t, right? Whatever that, if there are two signals R of t and C of t, I can add them and write it at the output. E of t is equal to R of t into this holds good in time domain. Similarly in Laplace domain, instead of R of t, the input is R of s, here it is C of s, another input, sorry, and output E of S is C of S plus R of S. I can write it, right? This is simple addition. Addition of two input signal holds good whether it is in time domain or Laplace domain. Similarly, in figure B, it is subtraction. You can observe here in time domain R of t and C of t. R of t and C of t is subtracted. Minus sign is here. E of t is R of t minus C of t. Similarly, in Laplace domain, R of S, C of S is here. E of S equal to R of S minus C of S. Addition is over. Subtraction is over. Next, third one is, you can observe it is, if there are here in figure A and figure B, you have seen two signals are added or subtracted. If there are more than two signals, let me take it. R1 of t is one signal, R2 of t is another signal, and C of t is another signal. All three with more than two signals. So R1 of t, R2 of t, and C of t is minus. So observe the sign here. C of t is subtracted. R1 of t and R2 of t are added at the summing point. C of t should be subtracted. So the output E of t is equal to R1 of t plus R2 of t minus C of t. This is addition of more than two signals. This is also addition operation. But the signals are more than two, greater than two signals, right? Similarly, this holds good in Laplace domain also. E of S equal to R1 of S plus R2 of S minus C of S. So you came to know the block diagram algebra, addition, subtraction, right? And one more thing you can see here, the addition and subtraction operation is linear. Whereas in the figure D, this figure D will go for multiplication. Multiplication of signals is non-linear. I'll tell you multiplication. Figure A, figure B, figure C, they are giving addition and subtraction operations, right? Whereas in figure D, we'll see the multiplication operation. Yes, I have signal R of t, I have signal C of t. I want to multiply. Then what is E of t? E of t is equal to R of t into C of t. Yes, we can multiply the signals in time domain, R of t into C of t. But it is not the same case. We cannot multiply the signals in Laplace domain. Suppose the input is R of S and another input is C of S. I want to, what is the output? E of S. If it is multiplication operator, it is convolution operator. R of S convolved with C of S. E of S is equal to R of S convolution of C of S. R of S convolved with C of S. So the addition subtraction operation remains the same in Laplace domain and time domain, whereas in multiplication domain, in time domain the multiplication operation is fine, but in the Laplace domain it is in the multiplication nothing gets converted to convolution. R of S convolved with C of S. You know the convolution operation, you have studied in S and S, right? Okay, fine. The next figure E I will not discuss here. I will go to the next slide. So in the block diagram algebra, what you have seen, addition, subtraction and multiplication in both time domain as well as Laplace domain using the summing point. Alright, we have seen this. This figure E I will discuss next. Yes, here I am discussing branch point. Another name for branch point is takeoff point. What is branch point or what is takeoff point? Just observe this diagram. So there is a single block G, right? Representing the transfer function inside it, G. Then R of t is the input and output is C of t. And here, there you can observe the node or point here. And the signal from this node is taken from the output and it is going to some other block. It may go to some other block. There may be some other block here, right? It may be going to some other block. And this point, we call it as takeoff point. And how to define this takeoff point? Or branch point. This point we call it as takeoff point or branch point. In the diagram it is visible, but how to define it, that I am telling. So branch point or takeoff point. So branch point or takeoff point is a point from which the signal from a block, signal from this block, right? Signal from this block goes concurrently to other blocks or summing points. It may go to other block or it may go to some other summing point like this. I hope you understood. Right, this point we call it as takeoff point or branch point. So it is a point from which the signal from a block goes concurrently to the other blocks or to the summing points. I hope you are getting, right? So this, we are using this terminology in order to identify the takeoff point or branch point. I hope it is clear. Yes, block diagram reduction rules, 13 rules are there. Okay, we will see there are totally 13 rules are there. We'll study one by one and we will try to understand all these rules. Yes, without these rules we cannot go for block diagram reduction. If there are multiple blocks are there, multiple feedback, I have to eliminate all those and make it single block, right? That I have shown here. Yes, I'll go back and tell you people. Yes, there are multiple blocks are there, multiple feedback paths are there, and I have reduced it, we have reduced it to single block consisting of input and output by using block diagram reduction rules. So those rules we are going to study now. So these are the block diagram reduction rules. So in this slide I have listed two rules, rule 1 and rule 2. We'll see one by one. It is not mandatory to remember all these rules. If you know how to apply, that is sufficient. No need to remember or reproduce these rules. Okay, you can observe the first rule, combining the blocks in cascade or series. Suppose the blocks are in series or cascade. Observe here, G1 and G2, they are in series or cascade, right? The input is X1 and the output of this block 1 you can see here, X1 into G, multiply, right? The signal that is coming into the block and the transfer function of the block, G1 into X1, right? Similarly, G2, out to the output I am getting the transfer function of the block G2 multiplied by the input signal X1 into G. So final total output is X1, G1, G2, right? So the blocks instead of G1, just in the second diagram you can observe here, instead of G1, G2 had come here, G2, G1. Yes, the blocks can be interchanged, no problem, right? G2 is here, G1 is here. Finally, the output remains the same, X1, G2, G1. Suppose the two blocks are in series or cascade, I can convert it into a single block like this. You can observe it. Just multiply the transfer function of the two blocks. G1 of S are simply G1 and G2 of S are simply G2. Just there are two blocks here. I merge them into a single block like this and multiply the transfer function G1 into G2. So here it is multiplied G1 into G2. I hope you are getting the transfer function and represent it as a single block. The input is X1 and output is X1, G1, G2. This is input and this is output. So the rule 1 says that we can combine the blocks in series or in cascade by using this rule. There are two blocks converted to single block, right? I hope you understood this rule. Combining the blocks in cascade or else combining the blocks in series. The blocks which are in series, just multiply the transfer functions and indicate the input and output. Then coming to the rule number 2, combining blocks in parallel. Observe here, G1 and G2, they are not in series here. In earlier they were in series. Here they are in parallel. You can observe here. G1 it is going and getting added to the summing point. G2 the signal goes in and it gets added to the summing point. So G1, if the blocks are in this fashion or in this arrangement, then the blocks G1 and G2 are said to be in parallel, right? At that time, how to handle these parallel blocks and how to convert them into single block. Just observe this diagram, this arrow mark I drawn here. Observe here, G1, there is a plus sign here. For G2, for summing point, plus minus is there. If it is plus, take plus. If it is minus, take minus. Generally, they are shown. So, if it is subtraction, subtract it. If it is addition, add it, right? We know the block diagram algebra already. So, from two blocks are there, I will make it single block. G1 plus or minus G2 has been converted and made it a single block. The input is X1, output is, this is input X1, output is X2. So, input X1, output is X2. I hope you understood these two rules. Yes, we'll study only rules today, and from tomorrow, using these rules, we'll try to solve the numericals. That is, I will give the set of block diagram, and we'll try to obtain the transfer function of the block diagram by using the block diagram reduction rules. So, how many rules it is possible to study today? We'll study. Rule 1 is over. Rule 2. So, rule 1 speaks about series blocks. Rule 2 speaks about parallel blocks. The next, rule number 3 and 4. Yes, in this slide. Yes, what is rule number 3? Moving a summing point after a block is rule number 3. Rule number 4 is moving a summing point before a block. Okay, we'll try to understand what actually it is. So, you know the terms summing point and block. You can see here, this is summing point and this is block. In the second rule, this is block, this is summing point. Okay. I want to shift the summing point after a block. I want to shift the summing point before a block. In the second case, we will see one by one. We will see the rule number 3, moving a summing point after a block. Summing point is here and block is here. I want to shift this summing point after a block like this. I want to shift it here after. So this rule tells moving a summing point after a block. Yes, what are the changes, but without affecting the functionality, right? Whatever the input I am giving, I should get the same out. The input is x1 and output is g into x1 plus or minus x2. I have to get the same if I shift also. That we will take care later. Just observe here. There is summing point, it is adding x1 and another signal x2. It may be, I can add or subtract plus or minus, generally they are shown. After the output of the summing point is x1 plus or minus x2, g is here. The output is g, the transfer function, multiplied by this input signal x1 plus r. So this is the output. This is input and this is output. So how to shift it? So how to move a summing point after a block? We will see this. Observe the next diagram, arrow mark you can observe here. Just simply shift it first. So G is taken here, first block is taken and summing point is drawn after. Means we have moved the summing point afterwards. So input x1 should remain the same. The output here, G into it should remain the same. Yes, we have drawn it. If I shift the summing point after a block, what will happen? Just observe, one more block gets introduced. This here, earlier x2 was passing directly to the summing point. Here, x2 is passing through this gain block G and it is added or subtracted here. Plus or minus, I am getting the same output. Whether how I am getting the same output, just check here. At this point, I am getting x1 into G. It is x1 into G plus or minus. Here I am getting x2 into G. So I am getting this output, right? x1 into G plus or minus x2 into G. Means if I shift the summing point after a block, just how to remember it I am telling. I have written here in green color. SAB direct gain block, SABD, you remember like this. If I shift the summing point after a block, it has to pass through the direct gain block. Direct gain block means, observe here, I am shifting the summing point after a block, right? Yes, it is coming here. But the signal x2, it is passing through direct gain block, G here. Right, this is gain block, right? This is the gain block. So if I shift the summing point after a block, the signal x2 has to pass through the direct gain block. X2 is passing through direct gain block and it is added to the summing point. I hope you are getting the summing point after a block, it has to pass through direct gain block. And in order to sum, if the summing point is moved before, this is rule number 4 we will see now. Moving a summing point before a block. Suppose the arrangement is like this. Block is here, summing point is here. I want to shift the summing point before a block. Here we have seen after a block. Here I want to shift the summing point before a block. What are the changes? Just observe here. The input here is x1. Output is x1 into G plus or minus x2. Right? And I want to shift this summing point before a block. So observe the changes here. Yes, this is the input x1, fine. And this is the output, it should be same. X1 into G plus or minus x2. I want to get this. Yes, this block is shifted here. Summing point is moved. Summing point before a block. Yes, summing point had come before a block. Block is here. So what are the changes? Here, if I shift the summing point after a block, it has to pass through direct gain block. If the summing point is shifted before a block, it has to pass through inverse gain block. Means G is there. Directly G. Here it is inverse 1 by G. Observe here, inverse gain block 1 by G. I hope you are getting 1 by G. If I shift the summing point after a block, it has to pass through direct gain block, right? If I shift the summing point before a block, it has to pass through inverse gain block. So I remember like this. If I remember any one, that is sufficient. SABD. Summing SABD I have written. Summing point after a block, it has to pass through direct gain block. SABD. S for summing, after, A for after, B for right before, and D for direct. Summing point after a block, it has to pass through direct SABD. So SBBI, summing point before a block, it has to pass through inverse gain block. If I remember this SABD, that is sufficient. I can easily recall this, right? So shifting the summing point after a block or before a block. You remember this is rule number 3 and rule number 4. Yes? Okay. Okay, we'll stop here because still we'll cover other rules. Yes, I'll stop recording.